All right, so we're back now. We've talked about our Bohr diagrams and how they show where our electrons are. And what's really useful for us is that we can look at where those electrons are and understand how it's interacting with light. All right, so electrons, right? Whoops, let's slide this all the way up here. There we go. So the greater distance from the nucleus, right, the greater the energy of the electron. So if electrons jump into a higher energy level, they've absorbed energy, right? Their energy is going to be higher because they're further away from the nucleus. Same idea for when the electrons fall. When they fall, now they're getting closer to the nucleus. They don't have as much energy, so they have released energy. Okay, so the big property of light that we really wanted to look at and to understand is that when electrons move, they're able to gain or release energy based on the visible light and that energy of light that it either absorbs or releases. Okay, so again, our waves are this electromagnetic radiation that we get to absorb or release. Okay, so particles for our photoelectric effect are just photons, and we can pretty much just kind of ignore them. We can say that it's either absorbed or released those photons. Okay, so our line emission spectra, what we have here is we have the absorption spectra and the emission spectra for hydrogen. Okay, so what happens with this visible light? Hydrogen is going to absorb certain wavelengths. We can see that there's really distinct black lines there, where if we had a broad spectrum light that had all the colors, only certain wavelengths are going to be absorbed by the hydrogen, because that's the only spots where those electrons are able to jump from one energy level to another. So the absorption spectra show the specific wavelengths of light being absorbed. Right? This is the amount of energy that is being absorbed when an electron starts at the ground state and jumps to the excited. When we have this emission spectra, you'll see that the emission lines line up with the absorption spectra. Right? Now the electrons are in higher energy levels, and it's going to be releasing that energy. So it's going to be releasing the energy and dropping down to a lower energy level. Okay, so our emission spectra shows the specific wavelengths of light being released. Okay, and it relates to our electrons jumping, right? This is why we know that they are traveling in these quantized orbits. All right, so the Balmer series, this is a specific type of electrons jumping, and it relates to our hydrogen emission spectra. Okay, so it has to do with hydrogen, and what happens is that it is when an electron drops energy, it's going to drop energy levels down to the second energy level. Okay, that's what these lines up here actually are. Okay, each of these lines represents an electron dropping from a higher energy level down to the second energy level. That's why the Balmer series is unique and is special for us, because we can see it in the visible light. Right? So how do we use those emission lines? We line up the lines. All right. Okay, so each of these lines is unique to hydrogen. There will be a different line, a different set of lines that will be unique to helium, and a different set of lines that would be unique to oxygen. Each element has a specific set of lines that tell us the energies of their energy levels. Okay, so looking at our energy now, right? what we have is a few different calculations that we can do with our energies, right? Our energies are related to wavelength and are related to frequency, okay? So our two equations that we want to use are E equals HF and E and C equals lambda F, okay? I'll also write frequency as the letter nu, which is kind of like a V, okay? So this frequency can also be the letter nu, okay? So the energy that we measure is always going to be in joules, okay? So whatever we have, our resulting calculation is going to be in joules. H is just a constant. It's called Planck's constant, okay? Planck's constant, it came out of when we kind of were starting to develop this quantum mechanics, okay? And it's 6.626 times 10 to the negative 34th joules seconds. You'll see here we've got joules times seconds, okay? Which seems really weird, but that's the thing, is it's a constant, so the units kind of don't matter if they make sense for us, but they are useful for us because they allow us to cancel our units, okay? F here is the frequency of light, right? So F or nu, okay? And it's a frequency is per second, right? It's how often something is happening per second, right? So S to the negative 1, right? S, our seconds would be in the bottom of our fraction, and it's waves per second. It's also called hertz, okay? Over here, C is the speed of light, right? 3 times 10 to the 8th meters per second. Then we have our wavelength. Wavelength, we generally measure in either meters or nanometers, okay? So meters and nanometers, they have the same base unit. Same base unit means that we can convert in between them using the nano scientific notation, okay? So 1 times 10 to the 9th nanometers is equal to 1 meter, okay? So using these equations, we should be able to calculate our energy from our frequency, or the wavelength from the frequency, or any of the other combinations, okay?